Okay, everyone. So first of all, many apologies to Francesco and to all of you for not being there in person. I would like to thank Francesco for accepting again our invitation to come in person to Naples and to give this course. I mean, I don't need to introduce Francesco to all of you. You know, he's one of the most widely renowned experts in nonlinear control theory. He has contributions to complex systems, nonlinear contraction theory, robotics, and many other fields. So it is a pleasure to have him here as also a board member of the Modeling and Engineering Risk and Complexity PhD program. And I'm very happy to see that many of you have joined online as well to attend this course. So without any further ado, I would like to leave Francesco the floor and thank him again for being here with us today.
Thank you, Mario, for the kind invitation. And thank you all for being here with me today. It's Friday, November 18th. It is my pleasure to talk to you about contraction theory and application to various dynamical systems. So this is a 10-hour set of lectures. It's envisioned as a mini course, but there will also be a reasonable amount of research ideas that may appear. I will use fundamentally three different sets of references. The first one is a set of slides, which I will share with you, and that I plan to present. It should be the better part of the first lecture. So these are a set of introductory slides, which you're seeing right now. After that, I am going to go back and do things carefully, one step at a time. And to do that, I will use my book entitled Contraction Theory for Dynamical Systems, which is right now available on my website. I'll share the slides as well. An early version of these slides may well be on my website right now already. And then after that, as time allows, I have a number of more, let's call them advanced topics that I have not yet introduced in my book. And so I have specific slides just about them. Right. And by the way, many apologies. My airplane did not deliver my suitcases, so there are things that I don't have. Apologies for the delay. My laptop and my iPad were playing tricks on me. All right. So what I'm about to show you, first step is the set of slides. These are introductory set of slides. I usually present them over an hour, but I'm going to go slowly today. So it'll probably take an hour and a half, maybe even two. We'll see how far we go. First of all, let me thank the people with whom I collaborated on research in these topics. And the research work is really what enabled all of the teaching work, all of the lecture notes. Specifically, Saber helped me a lot. And then since then, I worked on a number of topics with all of the others. All right, so what is the purpose? We would like to study dynamical systems, both in discrete time and in continuous time. These are my kids here, they changed all the colors. So here we have a discrete time system, and here it's a continuous time system, and we would like to study their dynamical properties. And I am especially interested here in strong properties in terms of stability over the transient and asymptotic. So these are well-behaved dynamical systems, those that are strongly contracting. We will then later study weakly contracting, semi-contracting, and all sorts of generalizations that allow you to capture even more examples. As a collection of examples, I will be inspired, essentially, let's see here, my kids are a mess. I will be inspired to look at networks. So a collection of examples will come from network systems. And so specifically, I'm going to be interested in understanding how, when you're looking at the dynamical network system, how does the structure of a network interact with the function of the network? So if you have a traffic road network, there's a certain structure with which place is connected with which other place. But the road network has a purpose, and the purpose is to allow people to travel from and materials to travel from one location to another. In the brains of animals, there are neurons that fire, and they're connected via synaptic connections. There is a certain topology to the network, which neuron is connected to which other neuron. Neurons have their own dynamics, and you have a dynamical network system. But that network has a function. It's not just existing because it exists, right? So you would like to relate the dynamics of the nodes, the topology of the network, with functionality. So here at the top are specific example of what I was mentioning. It may be coming from ecology. So it's well known that animals move together, execute motions together, whether it's flocking, swarming, and so forth. If you have a traffic network, or more generally a transmission network, or even another network is one in which, essentially in which materials is preserved, biomedical applications, you may ingest a medicine, and this medicine will travel throughout your body. So then you have a something called a compartmental flow system. So this particular compound is traveling from one location to another. Viral spreads, ecological interactions, coupled oscillators, and there's also interesting dynamics also occurring in social networks. And we would like to understand, we'd like to use network system and contraction theory as an excuse to study and understand the relation between structure and function. All right, so this is the slide where I introduce the theory of contraction for dynamical systems. So this theory is a robust version of Lyapunov stability theory. So many of you who have studied linear and nonlinear systems are familiar with the concept of an equilibrium and the Lyapunov function that allows you to establish the stability properties of the equilibrium. The Lyapunov theorem comes with various criteria. You could have a weak, a strong local, or a global Lyapunov function. Each of those lead to various stability properties. It could be that your function is on weakly decreasing, so now you have you apply the LaSalle invariance principle. So there's a standard theory of nonlinear systems. I like that theory. I adopt that theory. The theory that I am proposing for you is a robust version of it. It's a theory that, given a single condition, the contractivity condition, allows you to establish many properties. You prove one thing, you prove one property, and everything on this slide, those 5 properties, follow automatically. So on the right, there is an example of a very well-behaved phase portrait. You can draw phase portraits in 2 dimensions, but of course we want to establish these properties for arbitrarily large systems. In fact, interconnections, large interconnection of complex dynamics. So in this picture here, you see an equilibrium, you see trajectories, and you see the red boxes are level sets of a Lyapunov function. They're forward invariant sets, meaning to say, once the trajectory enters one of those boxes, it doesn't leave it any longer. Dashed red boxes. By the way, those level sets are drawn as squares. So this is a non-Euclidean Lyapunov function that I am plotting there, right? That's the infinity norm of the difference between your current position and the equilibrium. So in contraction theory, we will need notions of distances between points. And oftentimes that distance, that metric, will simply be the norm of the difference. But contraction theory works in arbitrary metric spaces, so that's very interesting. So what are all of these properties that automatically follow from the contractivity property? What are all these properties? Well, if your dynamical system is time invariant, then you're automatically guaranteed the existence of a unique, globally exponentially stable equilibrium. So your network could be composed of 1,000, 1 million, 1 billion nodes. It doesn't matter. Anywhere in this billion-size network, there could be a variation in a parameter. There could be a slightly different offset. There could be an edge that appears, disappears. Provided the contractivity condition is satisfied, you know an operating condition exists. A stable point, an equilibrium point exists. For example, in the study of power grids, there's always tremendous interest in establishing the existence of an operating condition. Do the active-reactive power flow equation have a solution? Can the power grid transmit the required amount of power to the customers from the producers? It turns out that our current power grids have limited capacity of transmitting power on any given line. Despite the topology, there is an ultimate upper bound on the amount of power that can be transmitted. The same is also true of freeways, by the way. On road traffic, if you try to jam too many cars into the freeway, it turns out that there's a traffic jam and the number of cars that manage to go from source to destination goes down. So there are upper bounds. So if you can prove contractivity in the regime where the system is contracting, you automatically know an equilibrium point exists. Please go back and read your books on stability theory, and you will see that the Lyapunov theorem starts by saying, given a dynamical system and given an equilibrium, if you can find the Lyapunov function, blah, 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 the equilibrium is usually given. But I'm telling you, in many problems, establishing the existence of an equilibrium is a problem on its own right. Sometimes it's even more important than establishing stability. All right. It turns out that if you satisfy the strong contractivity condition, you have two natural Lyapunov functions that always work for you. One of them is your distance to the equilibrium, and the other Lyapunov function is the speed, the norm of the vector field, the norm of the dynamics. Two very natural canonical Lyapunov functions always function. The distance to the equilibrium and the speed at which you're moving. If you see that you slow down, you are close to the equilibrium.
Which kind of distance?
The distance is the distance with respect to which your system is contracting. So I'll define everything very carefully. If you're working on a vector space with a norm, then the distance is simply the norm of the difference. So when I write, let's just write it out. Sorry, I need to keep fixing my colors here. The distance. This is what happens when you let your kids play with your iPad on a 20-hour flight. The distance between X and Y is simply the norm of the difference. So this formula always works if you have a notion of difference, so you're on a vector space, and you have a norm on the vector space. However, I could be living on a sphere, and the distance between 2 points could be the length of the shortest arc connecting the 2 points. On the sphere, you cannot calculate the difference between 2 points. The difference between 2 points is not a point on the sphere. But on the sphere, you can define a distance. There's a natural way of defining that. In fact, there are many more metric spaces than vector spaces. We'll see some examples. Okay, so I'll talk to you about these properties here. What are other properties? Robustness properties. So when I in my research, I had a chance to work with sociologists, neuroscientists, and so on and so forth. So people, and you're a control person, you're a dynamical system person, and you say, I would like to develop a model that is stable, that behaves well. When you talk to people that are not control people, they are going to imagine that when you say stable, you mean to say that, for example, if an input, if there is a disturbance and it's bounded, you would automatically assume that you get bounded outputs. And if your model, there's a little bit of unmodeled dynamics, you could assume that there's some little bit of robustness margins at least. And if perhaps there are delays when signals are transmitted from one location to another, then you would be robust with respect to that. So many of these properties do not automatically follow from the Lyapunov stability criteria, but they do automatically follow from the strong contractivity condition. Does that make sense? So when people say, oh, Francesco, please give me a well-posed dynamical system to describe my neuroscience model. Well, when they say well-posed, besides, they won't say that, but it's up to you to figure out what is it that they want. Then well-posedness may include all of these basic properties. Here's another basic property. If you have a periodic input that touches your system, so your system is subject to a periodic, maybe disturbance, then you would imagine that the behavior should be periodic. Don't you expect that? Right now, I'm going to try to shake the table, and I hope to see a periodic evolution. Maybe I have an animal that is swimming in water. All right, so there are some neurons inside the animal brain, or perhaps the neural system more generally, that are generating a periodic signal. This periodic signal is pushing the muscles to apply forces in a periodic fashion. Those forces are executed on the limbs. The limbs are pushing water. That's a highly nonlinear system, infinite dimensional, including the water. Why is it that the animal is moving in a periodic way? Is it true? How do you prove that? Well, I don't know how to prove it. However, I know that if the interconnection from the central pattern generators, which is the name of those groups of neurons that generate a periodic signal, from the central pattern generator all the way to the animal moving in water, if that interconnection is contracting, then it turns out that the main contraction theorem tells me, yes, it's true. Periodic input, periodic output. All right. Now, the next really nice thing is modularity and interconnection. So right now, I just showed you in one direction. What if you have a large network of nodes that are interconnected? And let's suppose that each of them is well behaved. So we have already studied each node, and you do know that each node is well behaved, is at least stable. Now, if you only know Lyapunov stability, now you are interconnecting them, it's quite complicated to now develop a general theory of stability for interconnected systems. In fact, I should say the reason I arrived at contraction theory is precisely because I was really keen on trying to get this right. I was interested in nonlinear interconnected systems. And so it turns out that, yes, you can work with Lyapunov functions. Now you're onto your own. You have a network of systems, you have a Lyapunov function for each individual component. How do you interconnect all the Lyapunov functions? That's a task. That's a complicated task. In contraction theory, there is a standard, very simple, very clean theorem that allows you to study, to give conditions under which the interconnection of contracting systems is contracted. So you would hope and you would expect that's the case. I will give you a test. It's something called a small gain test that allows you to infer contractivity of the interconnection of contracting components. Perfect. Finally, one other problem is, oh, okay, Francesco, you told me there exists an operating condition. I would like to compute it. If you have 10 states, this is trivial. You have a globally exponentially stable point. You start your preferred software, numerical software, or you work with Julia. You simulate the ODE, 10 variables. It's going to take a fraction of a second. You compute the equilibrium. Instead of having 10, you have 1,000,000. Okay, now you need to simulate a system that has 1,000,000 variables. What if you have even more? Now you need to find an equilibrium. You know it exists, but you really need to simulate everything. By the way, simulating an ordinary differential equation, the simplest numerical simulation algorithm is the Euler forward integration method. Like you're at the point, you take a forward step, and then you keep executing that very simple Euler forward integration. It has a step size. How do you choose the step size? If you choose the step size very large, maybe you get there fast. But if your ODE is stiff, it's ill-conditioned, you will not converge at all. So now maybe you need to execute maybe an implicit form, elaborate ODE solver for your stiff ODE. And now your ODE is the size of 1,000,000. That is not going to be easy. If your system is contracting, I can tell you the optimal step size for the Euler integration that will compute the fixed point for you. So, equilibrium point computation. And I should say the theory of contraction was born when numerical analysts were studying the solutions of ODEs. So, of course, contracting systems subject to inputs, for example, don't go to the equilibrium because the input could be forcing the system away from the equilibrium, but numerical integration of contracting systems is well posed and very accurate. All right, so these are all the properties that you get automatically if your system satisfies the strong contractivity property. So it's very fun and interesting and valuable to find the property, to understand what those properties are. I would like to also say one more thing. Again, on this comparison with the Lyapunov stability theory. It is true that if you give me a dynamical system, it may be easier to look for an arbitrary Lyapunov function rather than looking for a norm with respect to which the system is contracting. So basically, in both cases, you have to look for the right structure, the right Lyapunov function or the right norm. It may be easier because you have a larger set of Lyapunov functions to look for. On the other hand, it's a little bit like talking about an optimization problem. Not all optimization problems are convex. I don't know if you are familiar with the notion of a convex optimization problem. Not all of them are convex, but maybe in the right variables with respect to the right transformation, your optimization problem is convex. And if it is convex, then many, many good things happen. There are good algorithms, there is a global minimum, and so on and so forth. So in the study of optimization problem, there was a point in time, maybe 20 years ago, when people understood that the real difference was not between linear and non-linear programming. So linear optimization problems and non-linear optimization problems. The real difference was between convex and non-convex. Because if the problem is convex, then many, many things can be done. So I would almost argue, in fact, I will argue, that when you're dealing with nonlinear systems, the real difference is not that it's linear or non-linear, it's whether it is contracting or not. Because if it is contracting, as these properties prove, your dynamics is so well behaved that pretty much everything you want to do with it will work. All right. Perfect. All right, let me talk to you about his question.
Yeah, I have this last name. You explain later about how big is the pattern of
You're fantastic. I will respond to that by showing you some examples in the course of this mini course. I will also say, as I sort of hinted at, some systems are strongly contracting, others are weakly contracting or semi-contracting. So then there are weaker versions of these properties that apply. Yeah. Pardon me? Patience. I cannot just now start to tell you also. It is certainly not true that all systems are contracted. For example, if you start and you show me a cost function that has multiple equilibrium, that has multiple minima, and we're doing gradient descent on that cost function, then clearly the system is not contracted. It could be locally contracted. In fact, most likely maybe. All right. So let me. So we'll work out. We'll see some examples. So let me talk to you about the history. So in 1922, exactly 100 years ago, in fact, go backward even more. A couple of years before 1922, Stefan Banach was just an unemployed, uneducated person studying mathematics on his own. And then apparently, so the legend goes, Steinhaus, a mathematician walking on the park, met him and heard him talk about Lebesgue integration with another mathematician. A couple of years later, in 1922, Banach published his PhD thesis, and shortly thereafter became assistant professor, full professor, founder and director of the Polish Mathematical Society, just within the range of a couple of years. So his paper, 1922, is the paper where the Banach contraction theorem was established. Theorem 6 in this paper mentioned here. I have the PDF if you guys are interested. So the statue there is a statue that you will find in Warsaw if you go to this particular park where this mythical meeting took place. So that was about 100. This was exactly 100 years ago. Actually, the meeting was 100 plus, but the paper appeared 100 years ago. That's the PhD dissertation of Banach. A few years later, when people started to think about integrating differential equations and studying their numerical properties as computers were coming to be in existence, Lodzinski and another paper I'm not mentioning here, the PhD thesis of Dahlquist, are the ones that established the study of continuous time differential equation and their contractivity. Control people showed up in 1972, so 50 years ago, the date. Charlie de Soer and one of his students, Aneda, published a paper in the Circuits and Systems Transactions precisely on this set of tools. That's already a fantastic paper. It already talked about Euler integration and optimization problems to be solved using what I would now call contraction theory. So after 1972, people in the control area did not pursue these ideas for a good while. And it was until 1998 when Lohmiller and Slotin published a landmark paper which started the investigation of this area in more serious detail. One thing I would say is that people have studied contracting dynamical systems in the literature using different names, many different names for the same problem. And that's another reason why this theory has not coalesced and become more established until, I would argue, more recently. Finally, here in town, Professor Di Bernardo, Professor Russo, and others wrote this wonderful survey in 2016. There are many surveys by now that are available. I can share with you the full list. One of the other ones that I think it's important is this particular one by Giesel, Hafstein, and Cowan, where numerical methods are presented to verify contractivity with respect to arbitrary state-dependent metrics. So let me just say that I will present the theory, but I will not have a chance in my mini course to tell you about computational approaches. But there is a wonderful survey you can consult, and it's mentioned here. Now, also, it is a special pleasure to be here in Napoli delivering these lectures, because it turns out that while Banach published his paper in 1922, about 30 years earlier, Banach's theorem did not arrive in the middle of absolutely no knowledge, right? Before the work by Banach, there was the work by Picard. So Picard was already studying the method of successive approximations and conditions for its convergence, which are pretty much the Banach figures. And shortly thereafter, also the Napolitan mathematician Renato Cacciopoli also published a wonderful paper in 1930, exactly on the same topic. In fact, to be precise, to the best of my understanding, which is limited, I haven't studied the original papers in detail. The Banach paper is in French, and the paper by Cacciopoli, I haven't been able to get my hands on it. But the Banach paper is about norm vector spaces. whereas the paper by Cacciopoli is on arbitrary metric spaces, if I understand the distinction. And another wonderful historical tidbit is that he actually worked in Padua as well, my hometown. So that's wonderful. Wonderful history. Anyway, so some people in the literature refer to the general version of the theorem, which I'll show you, as the Picard-Banach-Cacciopoli theorem. Now, I was asked about examples. In this slide are 2 bits of information. So over the last 100 years, people have studied nonlinear network systems as they arise in a broad range of different disciplines. Lotka and Volterra studied population dynamics in the 20s and later. Matrosov and Bellman started the study of interconnected systems in the 60s. Kuramoto designed his famous model of coupled oscillators, which is one of the most expressive models of coupled systems that displayed synchronized oscillations. He did that in 1975. Just a year later, Lymanovich and York, mostly York, developed and mathematically analyzed the first interconnected model for multi-group epidemics propagation. I should say there's a scientist called Grossfield and Grossberg and Cohen, even before Hopfield. But okay, Hopfield in the early 1980s developed the most commonly adopted model of neural networks. In the 90s, D'Aganzo developed a model for traffic networks, the celebrated cell transmission model. And in the same time frame, Chua was developing diffusively coupled dynamical systems. So when I was trying to find a common thread in the study of these systems, I tried various theories, for example, dissipativity theory, or just generically the outcome of stability theory. And that's when I found it compelling to adopt contraction theory. And the reason being that, in fact, using either strong contraction in a number of examples, or strong semi-contraction or weak contraction, I'll talk about that later on, indeed, one can provide a unified language with which all of these examples can be analyzed. So the purpose here, for those of you who are so inclined, is to try to give a unifying language that works out in all the examples. Now, to be clear, not all of those systems are strongly contracted. They have various versions, typically weaker perhaps, than the full set of properties that I showed you 3 slides ago. All right, so the text is available on my website. The quote that I like by Mark Twain is that continuous improvement is better than delayed perfection. So when you're writing a book, you could spend your lifetime writing it, and you finally write it. And then you hate the subject so much that you don't touch it ever again. So I've done that in my first book. Here instead, that's not what I'm doing. What I'm doing is that I decided to publish, it's a little bit like software. Push it out early, get some feedback, and keep it improving. And this is, you can do this nowadays in 2022. There's something called print on demand self-publishing. And so at the end of this class, most likely, I will collect some feedback either from you or even for just my own teaching. I will make some changes. In fact, I was changing my book last night and this morning, in fact, even an hour ago. And then one of these days, maybe a month from now, I will upload the PDF. And if you order the book from Amazon for 20 euros, you get a printed copy of the lecture notes. Otherwise, you download the PDF on my website and it's free. Now, all right. I have spoken for 30 minutes. I think it's a good moment to take a 2-minute break. This was the introduction. And then after now, I'm going to actually write equations, start to show you what happens. I'll let the system record. And for the reason being that if I suspend it, I inevitably forget to turn it on again. So So just be aware that it's recorded. And let's take just 2 minutes. Okay. Perfect. All right. We are almost back. Let me give a fair warning. All right. So let's now start the technical treatment. And again, I think it's good if I give you the introduction first as a motivation. And if you know, that way you get something out of it, even if you don't come to later lectures. But this has a drawback. Then we're going to go back and we're going to start the book chapter by chapter. So there will be a little bit of redundancy with what I do later. But okay. So here's the way I'm going to do it. I'm going to start with the discrete time. And the reason being is that it's easier and more natural. And it's very closely related to something that you should know, Lipschitz constants. And it allows me to review the standard Banach contraction theorem. And then we generalize that to continuous time. And then from continuous time, we're going to, from systems that have no inputs, we're going to go to system with inputs. And then from single systems, we're going to go to network of systems. So start with the simplest case and then show various extensions. And I should really have another one saying from deterministic to stochastic and from ODE to PDEs. But I'm not good enough. I haven't had a chance to write those slides yet. But there are theories out there for stochastic systems, for PDE systems, and so on and so forth. It's just my inability to present it to you today. All right. So first of all, we need a notion of distance, which will be the difference, well, which will be the norm of the difference, because right now we are dealing with vector spaces. But keep in mind that this can be generalized to arbitrary metric spaces. Now, you're well familiar with what's written on this slide, I imagine. If not, you absolutely need to go study this after the end of this class. On the left are 3 basic vector norms, and in the middle column of this table, the right column we'll do later, are the corresponding induced matrix norms. Now, let me just comment that the Euclidean norm is the largest singular value. So you need to look at the largest eigenvalue of A transpose A and then take a square root, bring it back. And in fact, instead, whether you have one or infinity norm, the induced matrix norms, you take the absolute value of the matrix, meaning to say the absolute value of each entry. And then you do, in one case, you sum over the columns, and in others, you sum over the rows. And I don't remember that by heart. I get confused all the time. So how do you do that? You look at this Aij is the arbitrary ij entry. If you keep j fixed and you sum over I, that means you're summing over the column. And then you look at the worst column. And here you look at the worst row because you're keeping I fixed and you're summing under j. If you sum under j, that means you keep the, you sum under. I wrote it here, so this is column and that's row sum. In one case you do the column sum, in the other you do the row sum, and you need to figure out a way in which you can remember that, because I clearly am unable to teach that to you. Now, okay, so these are simple formulas that, other than my distraction, they're straightforward. All right, so let's talk about discrete time dynamics and Lipschitz constants. So I have a discrete time dynamical system, capital F, described by the map F, and it's on Rn, so standard Euclidean space, nothing fancy. I have the norm on the space and the induced norm on the space of matrices, and I use the same symbol for both. Okay, some authors use different symbols. It's the same. Now, what do we know about this setup? We know that there's something called the Lipschitz constant of the map F. What is that Lipschitz constant? Well, it's about bounding the variations, right? So if I have a variation in xy, then the variation in fx minus fy, they're related by this upper bound with the constant L, lowercase l. Lipschitz, well, it's a positive number. So if I vary the input, the output varies, but not more than L times the variation in the input. Lipschitz constant, right? Standard. This is the global Lipschitz constant. You can also define a local version over a certain set, and we can talk about contractivity over a set, which in fact I'm going to talk about in chapter 1 of the book, not in this slide, in the book that we'll do later. Now, this is the standard notion of a Lipschitz constant. Notice that it has to be non-negative. It could even be zero, of course, if you have a constant map. But okay. In fact, I wonder if this is a typo, but I'm taking the inf, so it could be zero, but I should maybe allow L equal to 0 there. Now, there is a theorem, Mark. No, the norm is fixed. I fix a norm and I fix a map F, and the Lipschitz constant of a given map F with respect to that norm is given by this maximum variation. Now, here I wrote an equality. The first equality, that's the definition. The second is a theorem. So I'm not going to go into the proof right now, but just to be clear, one is a definition, and then it's not obvious that the first row is equal to the second row. Oh no, you need to work for it. In fact, the first row is well defined with the Lipschitz property implies continuity. In fact, people also say Lipschitz continuous. The second row requires differentiability because now I'm actually computing the Jacobian of the map F. I'm using the Jacobian. In fact, it turns out that you can, well, let me just leave it at that. Although I will say that the second row, this expression here, is still well closed, even when F is only locally Lipschitz. When F is locally Lipschitz, it's known to be differentiable almost everywhere, which means that the Jacobian is defined almost everywhere, which means everywhere except for a measure, except for a set of measures 0. So it turns out that you can define the Lipschitz constant of F to be something called the essential supremum of the norm of GF. I'll come to that in a second. where this is essentially almost everywhere. So wherever the derivative is defined, you look at what happens. That's still fine. That's still the Lipschitz constant. So you don't need differentiability. You can use the derivative almost everywhere. Now, but let's get to the heart of the formula. It's derivative of what? So here you need to keep in mind three concepts. You take the Jacobian, the norm of the Jacobian, and the supremum of the norm of the Jacobian. So it's a mouthful to remember. But the Lipschitz constant is the supremum of the norm of the induced matrix norm of the Jacobian. Does that make sense? So you give me the map: Jacobian, induced norm, supremum. Three operations, one after the other. All right. And these are the same. Notice that the second condition is pointwise. The first condition is a condition about pairs. Interesting. Now, if the map F, capital F, is scalar, lowercase f, then the induced norm is just the absolute value. So now, not a big deal. The Lipschitz constant is the supremum of the absolute value of the derivative. It's not a Jacobian, it's just a derivative. So, I don't know, you could have a map. You could have a function that goes up and down, something like that. You compute the derivative, you take the absolute value. So the Lipschitz constant is an upper bound. So the Lipschitz constant of f is greater than equal than f prime at any x, and also minus f prime at any x. Is the max of this. So, right, it's a derivative, an upper bound and a lower bound. Okay. It turns out that I'm interested not just in scalar maps, which are not all that interesting. Let me be interested for a second in an affine map. An affine map is described by a matrix A and a vector B. B will play no role at all. The matrix A will play an important role. So what is the Lipschitz constant of an affine map? Okay, I now need to choose my norm. And I'm gonna consider two choices. I will consider this weighted two norm. How do you define a weighted two norm? You need to give me a positive definite matrix P. Square, symmetric, all positive eigenvalues. That's a positive definite matrix. You take the quadratic form, x transpose px, and that's your transpose there, and that's your norm. It turns out that, according to this formula right there, the Lipschitz constant of f. Well, I'm writing. What am I writing? I'm writing 2 sub p to describe that norm. So the Lipschitz constant with respect to that norm, I'm writing f sub a to denote that f sub a. According to this formula, I should take the supremum over x of the induced norm of the Jacobian. But the Jacobian of fa at each x is just a, right? The Jacobian of ax is just a. And now it doesn't depend upon x, so I don't have to take the supremum. So it's just the induced norm. So I get the induced norm of a. Does that make sense? Let's play the other game. Suppose I use this infinity norm. The infinity norm is also called the max norm or the sup norm. It's very useful in many cases when you want to upper bound the error, you know, each entry of the error. Whereas if you have a two norm now, yes, it's conservative to go back to upper bound on the normals of each entry of the error. All right, so let's make this a little bit bigger. So all the same thing happens. The Lipschitz constant with respect to the infinity. Oh, by the way, I apologize, I was forgetting. I'm going to use a weighted infinity norm in general. Eta will be a vector in Rn with n entries, all positive. They have to be positive, otherwise that norm, if any one of them is negative, then it's not a norm anymore. The norm is always non-negative. It can never be negative. All right, so I will use the L1, L infinity norms. Whenever I use them, it's just as natural and convenient to use diagonal, to use weights such as this, a vector of weights. For the two norm, it's natural to use a positive definite matrix P. Those are the common cases. Now, here, I also placed another additional theorem. Suppose that I want to get a condition that ensures that my either 2p norm or infinity eta norms are upper bounded by some number, L. Okay, then 3 slides ago, I had written these formulas here, remember? And you agreed that these were relatively standard, other than my inability to remember if it's a row or column. It turns out that even those formulas are correct, and you can use them like that. With very simple algebraic manipulations, you can show that, and it's well known, that these things are equivalent, 1 and 2. So asking for an induced norm to be upper bounded by a constant becomes an LMI, a linear matrix inequality, if you are working with the 2p norm, or becomes a linear program, LP, if you're working with the infinity weighted norm. Does that make sense? Now, these are relatively well-known facts. The proof is in the book that you can download. If you have questions, you have doubts, we can work them out together. It's not too hard. It's a couple of lines of matrix theory. It's not rocket science. Okay, it's rather straightforward. Okay, so upper bound on the induced norms, which themselves are Lipschitz constants, are solutions are given by linear matrix inequality, LMIs, or linear programs. LMIs and linear programs give rise to convex optimization problems. They're usually very nicely solvable. LMIs can be solved in the size of a few to several thousand variables on normal size computers. Linear programs can be solved in the size of millions to hundreds of millions of variables on a normal size computer. So linear programs are very scalable. Okay. Now, finally, I'm ready to remind you of the Banach contraction theorem. What does the Banach, this Marvel called the Picard-Banach-Cacciopoli contraction theorem, what does it say? And here, in order for me to be consistent with the slides that follow, I'm calling this the Banach contraction theorem for discrete time dynamics. But the reality is that this is the Banach contraction theorem, essentially. It says the following. Oh, this is over a normed vector space. It says the following. Suppose that the Lipschitz constant is strictly less than 1. So the variation in the input gives you a variation in the output, but the variation in the output, the size of the output, is strictly less than the constant, well, it's less than equal than a constant less than 1 times the variation in the input. Then that map is called a contraction, or is said to be contracting. And what that means is that the distance between trajectories decreases exponentially fast. Perhaps the derivation is that if you start with any two different trajectories, y0 and x0, then you could say that the distance between f at time, well, let's say time 1, pardon. No, actually, let's do it even better. X at time 1 minus y at time 1 is equal to f of x at time 0 minus f of y at time 0, which is upper bounded by L, which we know is strictly less than 1, which multiplies x at time 0 minus y at time 0. So now I've gone from a bound at time 0 to a bound at time 1, and it's multiplied by L strictly less than 1. So, of course, believe me that many formulas are true. For example, sorry, that's y at time k is upper bounded by L to the k, x at time 0 minus y at time 0. L is less than 1, L to the k is going down to 0 exponentially fast. We will see the very general formula for the Banach contraction theorem, and there are there are going to be three interesting bounds that I've been showing you. This is just one of them. So you don't have to remember this by heart right now. So I have pictured this. I have shown x, 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 right? You see this? And then I have shown it for y. They're coming together. And I am drawing, well, I decided to use the L infinity norm just for fun. So I've drawn a square, a ball. It's a ball, it's a square ball in the infinity norm, centered at the solution x. And this, let's call that a radius. That radius is shrinking exponentially fast. And the property is that the y trajectory is inside that ball. It cannot go outside. You start with the ball is shrinking, and all the trajectories start inside the ball, come with you. They don't go away. That's the first line of the theorem. Any questions?
Yeah, I understand you are working in RM.
Pardon me?
We are working in RM.
RM.
We use it as school.
Right now, the full RM. Yeah. Yeah.
So we can use this machine.
It's complete. Yes, you're completely correct. The key secret here is that it's not a secret. The key idea by Banach in his theorem is precisely that essentially here we're proving that the sequences are Cauchy, and then because the space is complete, a point must exist. Yeah? Now, that was the next step I was going to make it. So let me make it now. So let me erase these calculations. So that was the first row of the theorem. What the theorem says is that the main part of the theorem is that there exists a unique equilibrium point x star or fixed point x star. So here I should draw it. I have not drawn it. So here there is a point. That point is called x star. It exists and it's unique. And it is globally exponentially stable. What that means is that not only from y naught and x naught, but really from any other arbitrary initial condition, all trajectories are converging to x star exponentially fast. It's contracting from everywhere. Does that make sense? This is my animation of the theorem. I am drawing trajectories as lines. I should be drawing them as dotted points because it's a discrete time. They're all converging from everywhere. And on top of that, those bounds that I just erased would be telling you that there are balls around x star. And once the trajectory has entered one of those balls, it remains inside. So that's what the theorem is telling you, more than the picture is. So I drew the picture and I wanted to complete it. Perfect. So this is a simplified statement of the Banach contraction theorem for discrete time dynamical systems. Now, I would like to make a jump and talk to you about continuous time systems, going from discrete to continuous. So I want to show you the continuous time version of the Banach contraction principle. To do that, I need a little bit of tool, a new tool. Actually, I need two new tools. Let me introduce one new tool, one at a time, of course, right? The first tool I want to introduce is called the induced matrix log norm. So remember, earlier I reminded you of the definition of the induced matrix norm. So this is the induced matrix log norm. Log norm. So induced norms in discrete times, log norms in continuous time. The log norm here, this definition seems a little bit scary. You're taking a limit with an h at the numerator and denominator. In fact, it's essentially a derivative. It's the derivative, it's the directional derivative of the induced matrix norm at the identity in the direction of the matrix A. I've said it verbally, but that's what that limit means. That formula may appear to be a little bit scary. I should prove that it's well posed. I should develop more intuitions for it. Not needed. In a first approximation, all you need to know is just that, just like before, Before, there was a definition of the induced matrix norm. I didn't even remind you of the definition. It was not all that relevant. I just told you there are formulas and you were okay with that. So now I'm arguing to you for the induced matrix log norm, there are formulas, just like before. They're very similar, actually. They are very similar. They're different, they're similar. For example, before we had to compute the largest singular value of the matrix A. So it was A transpose A, lambda max, and then I can take the square root to go back from A squared to A. Here, you don't take the product of A, you take the symmetric part of A plus A transpose divided by 2, and you take lambda max of that. So it's the largest eigenvalue of the symmetric matrix A plus A transpose. Remember, when the matrix is symmetric, the eigenvalues are real. Are real, not positive. In general, no, that's not true. Before, for the 1 and infinity norm cases, we had max column sums and max row sums with the absolute value. Now, it's very similar. You still have row sums and column sums. You're still summing under I here, just like it was there, and it was J and it's J here. So it's the same column for the 1 norm and rows for the infinity norm. But here, you take the absolute value only of the off-diagonal entries. You do not take absolute value of the entries on the diagonal. The entries of the diagonal are outside the sum. That's very helpful because it turns out that if I give you, for example, the matrix minus identity in dimension n, then you will see that all these 3 formulas will give you that mu of this is equal to -1. Well, why is that the case? Well, the off-diagonal entries are all 0, so this is 0. That's 0, and -1, max of entries all equal to -1, it's -1. And then if I do A plus A transpose divided by 2 of a symmetric matrix, the identity is symmetric, you get the matrix itself. And then the largest eigenvalue of the matrix equal to -1, well, it has n eigenvalues or equal to -1, right? Notice that it's negative, right? Whereas here, if I were to take the induced norm of minus identity, you will see it's always equal to +1, no matter what the norm is. Because the norm was defined in a different way. The induced norm of a matrix is defined as the maximum value that the vector AX may take divided by the norm of X when X is different from 0. And so the induced norm is always positive or 0. Whereas the induced log norm can be negative. So I want to clarify one thing. The log norm is not a norm, it's a logarithmic norm. It has different properties. The norm is not negative. The log norm can be negative. Can be negative.
Just wondering what is like the simple equation of
Yes, yes. Let me give you this intuition. In discrete time, when I have xk plus 1 is equal to axk, and x is real, it's just a scalar number. Then then a less than 1 implies that x goes to 0 as k goes to infinity, right? In discrete time. In continuous time, I will use the letter k for discrete time and t for continuous time. In continuous time, x dot equal to ax of t. Then what do I need in order for x to go to 0 as t goes to plus infinity? I need a less than 0. And notice that here I took the absolute value and here I did not. So I need an operation that captures the fact that something can be negative. And this operation, So here's another way to think about it. In discrete time, if I have multiple roots, multiple eigenvalues, I need them in order for stability to live inside the unit disk, right? So more precisely, I need the spectral radius of the matrix. I need rho of A be less than 1. In continuous time, I need the eigenvalues to be on the left up plane, right? They need to be on the left up plane. Sorry, it didn't complete here. Let me try it again. I'm really fond on my software here, but I need to close my boxes there. They need to be on the left. So another way to put it is that the spectral abscissa, they need to be to the left of it. So what do I want to do? I want to change these colors that my daughter has changed here for me. So it turns out that rho of A is always upper bounded by the norm of A, and alpha of A, the spectral abscissa of a matrix. The spectral abscissa is the largest. So this is equal to the max of the real part of lambda, where lambda is an eigenvalue, right? Spec A is the spectrum of A. Lambda belonging to spec of A means it's an eigenvalue. The maximum real part. This is upper bounded by mu of A. So log norms are upper bound on the spectral abscissa. Induced norms are upper bound on spectral radiuses. In discrete time, you use spectral radiuses and induced norm. In continuous time, you use spectral abscissa and induced log norms. We're going from discrete to continuous. Okay. Now, let's go back. I want to define this new operation. Given a matrix, I get a number. The number can be negative. But it turns out that, to some extent, this new operation has very similar properties to the old ones. And the ones that are identical are stated here. It's subadditive, it's scaling property, and it's convex. And I want to remind you, although I forgot to say it earlier, that the induced norms of A plus B is upper bounded by the induced norm of A plus the induced norm of B, the induced norm of a scalar B times B, or I should say, I should have written A, sorry. I should have written A. So let's say I have a scalar here, beta times A, it's upper bounded by the absolute value of beta times the norm of A. And these two properties together give you convexity. So if you have the absolute value of theta A plus 1 minus theta B, where theta is a number between 0 and 1, this is upper bounded by theta, the induced norm of A, plus 1 minus theta, the induced norm of B. So the induced norm is subadditive, positive scaling, and convex. The induced log norm has essentially the same three properties, with the difference that, let me let it. It's exactly the same three properties. So if remember, the point is that I just wrote it slightly different. When you bring out beta, it becomes absolute value of beta, or equivalently. Or equivalently, here this property is stated for B greater than 0. So induced matrix norm, induced matrix log norm have many similar properties, but they also have substantially different aspects to it. Again, the induced norm is an upper bound on the spectral radius. The induced log norm is an upper bound on the spectral abscissa. In the book, there are entire careful classifications of all of the similarities and all of the differences. Okay. So now, I'm ready. Question. Submultiplicativity. Submultiplicativity holds for induced matrix norms. They are, it's not a property that you would look for when you're studying induced log norms. We'll come to that. We'll come to that. Now, remember I've done 2 slides for the discrete time case. All right, discrete time system, Lipschitz constant for it, And then I had the following slide was the contraction mapping theorem for discrete time system. So now I have two slides for the continuous time case. Are you ready? Works like this. I have the same F, but now it's in continuous time. I am still in Rn. I still have a norm. And now I have an induced log norm instead of an induced norm. Entirely parallel. Now I need to define the equivalent of the Lipschitz constant. And the equivalent I will call the one-sided Lipschitz constant. Some people also call it the log Lipschitz constant, but let's just say one-sided. I'll go with that for today. The one-sided Lipschitz constant, I should define it, and then I should give you a condition on the Jacobian. For now, let me go like this. I'll skip that part in gray. I'll come back to that later. Let me define the one-sided Lipschitz constant, OS lip, using the differential characterization. What do I need to do? I need to compute the Jacobian of F. I need to take the log norm of the Jacobian of F, and I need to take the supremum of the log norm of the Jacobian. So this is the same story as before. Before we take the supremum of the induced norm of the Jacobian. Now I have the supremum of the induced log norm of the Jacobian. See, it's very, very similar. I substituted log norm for Jacobian. We have an unwelcome best. Now, why is it called one-sided? Because of this simple equation here. Before, I want to remind you, we had lip f equal to supremum with respect to x of the absolute value of f prime of x, right? Remember? And I said to you that the Lipschitz constant was an upper bound on the derivative minus the derivative. It was an upper and lower bound. Here, we are only interested in upper bound, one-sided bound. Does that make sense? One-sided bounds only. What if I were dealing with in a affine map? What would things look like? Okay, I have FA of x, which is ax plus b is a vector, b plays no role. The one-sided Lipschitz constant with respect to the 2p norm, or the one-sided Lipschitz constant with respect to the infinity eta norm. What are they? Well, according to this definition, I should take the Jacobian, but the Jacobian is just going to be the matrix A. And I should take the supremum over x, but the supremum over x, the Jacobian is dependent upon x, so it's the same object. That's just equal to the log norm of A. And as before, there's another theorem. So again, let me remind you. So here, I'm basically writing two steps here. I apologize. It's my... The first theorem is this. Well, the first calculation is that. That's the first calculation. Moreover, I'm also telling you, suppose I wanted the one-sided Lipschitz constant to be upper bounded by a constant L. How do I rewrite that? Well, like before in the discrete time case, it turns out that the 2p norm case gives rise to a linear matrix inequality, and the infinity eta case gives rise to a linear program, a linear set of inequalities. Before we had A transpose BA less than equal than LA. No, sorry, less than equal than LP. Forgive me. And then later on, we said for stability, we wanted L less than 1. This is called the Stein stability LMI. And this one is called the Lyapunov stability LMI in discrete and continuous time respectively. This these other equations here, this equation here, this dagger equation does not have a name. It's just a linear program, a linear inequality, telling you when is it true that the matrix A has induced gain less than L. Okay, now Now we've defined the one-sided Lipschitz constant, and here is the long promised Banach contraction theorem for continuous time dynamical systems. To be honest with you, I am even surprised that this theorem has not been carefully articulated and been written and established for a long time. In my mind, well, people have known this for a long time. It's just that it hasn't received the amount of attention that you would normally expect. You would expect that somebody would have stated, written a book on stability and would have done the discrete time and then the continuous time case, right? All right. So I want to tell you that here I just cut and pasted the statements from before. This is really identical to before. What changes have I made from before? Oh, there's an OS there. I added the OS because we're in continuous time rather than discrete. Oh, I wrote continuous there instead of discrete. That's OS. Oh, there's one more thing. I decided that I should call this infinitesimally contracted instead of contracted. Why? Because F is the vector field, so its flow is contracted. As soon as you move infinitesimally, the distance is decreasing infinitesimally. So in continuous time, I will try to remember to use the language infinitesimally contracted instead of contracting. But okay, you know, many people in the literature are not that careful. You just say contracting, and people more or less understand it, but still. Now, it was my pleasure to draw this picture with lines instead of dots. I also left the dots just to remember at that particular instant of time, I have drawn the box. But really the trajectories now exists for all time. And what does the theorem say? The theorem, statement 1 says that any two trajectories are infinitesimally convergent to one another. And then the theorem says that there exists a unique point x star, and no matter where you start around it, all trajectory converge to it exponentially fast. And just like before, if I draw boxes around it in the right metric, in the right norm, the boxes are forward invariant, and they're the level set of a Lyapunov function. Does that make sense? Just like before. Question?
Yeah, just for the clarity, before the process was xn plus 1 is equal to f of xn, and now the process is x dot is equal to fx.
That's correct. Yeah. Before we were studying xk plus 1 equal to f of xk. And now we've gone to x dot equal to x dot of t equal to f of x of t. Does that make sense? Same theorem. But in continuous time, I need the log norm. I'm sorry I have to introduce it. I would like to do without, but I need it. I cannot state it without. Now you should ask me, Francesco, what is this statement in light gray that you have there? I really like that lip f equal to the inf of L greater than 0, such that fx minus fy less than equal than Lx minus y. So here I wrote for you the definition of the Lipschitz constant. Right? The definition of the Lipschitz constant does not involve the derivative of the map, the Jacobian. The definition uses the notion of a variation. It's a theorem that I give you the condition of equivalence with the supremum of the induced norm of the Jacobian. But here, for the case of the one-sided Lipschitz constant, what is the condition that does not involve the Jacobian? How do you write that condition? In order to write that condition, which is here in gray, I need to introduce to you one more concept, a little detour. What is this concept? I need to take the inner product. So you guys know what's an inner product, right? Inner product. What's the inner product? So I could write, some people write x, y. Some people write double bracket, x, y. X and Y are elements of Rn, they're column vectors, so it's just X transpose Y, okay? The dot product between X and Y, it's just the transpose of the first into the second. It's an inner product, right? I decided I was gonna go use the double brackets. I don't know why, but okay, bear with me, double brackets. So we'll use this notation, not this, I'm gonna erase this, okay, fine. That's an inner product. What properties does the inner product have? Do you remember? If you look at it, you can quickly guess it. It's linear, it's bilinear. In both arguments, it's bilinear. You can scale both arguments, right? And it satisfies the Cauchy inequality with respect to. Another thing is that x into x is equal to the 2 norm of x squared. So it's compatible with the 2 norm. The standard inner product is compatible with the 2 norm. They come together. They're like cousins. They like each other. Now, I need a way of computing inner products when, instead of dealing with the 2 norm, or maybe, oh, by the way, let's do the P norm. So if I have 2 comma P, this is just X transpose PX, right? Let's put a square on the left-hand side so we don't have to take the square roots. The 2 comma P. No, that's not correct. I need a square there, and the reason is that I use this definition. When I have a P there, I need to say 2 comma P. That's just PX 2. So then I have PX transpose PX, and then it's X transpose P square X. So in the literature, when people define the weighted 2 norm, there are 2 different conventions. The one that I am adopting here is not the most common. Okay, I will agree with you. The most common convention is to use a subscript matrix. But people actually really write this. They write P, and that's X transpose PX. But if I write 2 comma P, then I mean this convention here. Okay, so I mean to say I want the P to go inside. All right, now I need to generalize the notion of inner product to spaces where the norm is either the 1 norm or the infinity norm. In fact, arbitrary vector spaces and arbitrary norms. I need to define a notion of inner product. And what is the key property that I need to maintain? I want this property to hold. What is this property? Let me show you what I mean. So if you take the time derivative of the 2 norm of x squared, what is that? So then this is just the time derivative of x transpose x. And I can use the product rule. And what do I obtain? I obtain x dot transpose x plus x transpose x dot, right? So then this is equal to twice x transpose x dot. Does that make sense? Very simple. So if you have the 2 norm, it's easy to compute the derivative of the norm. The derivative, now I'm assuming that x is a function of time. And I'm taking the derivative with respect to time. So x is a curve. And I want to take the derivative of the norm along the curve. So this formula here is the derivative along a curve. Derivative along a curve. It's very easy when you have the 2 norm. If you want to eliminate the 2 from here, you just divide everything by 2, 1/2, 1/2, 1/2. So the 2 is convenient, so you don't have the 2 to carry along. Now, in the end, the outcome here is that this is the inner product between x dot and x. So derivative along the curve is x dot inner product with x dot with x. Now it's natural that it would be linear in x dot because you have a function of x is changing. You take the derivative with respect to time. it should depend linearly on x dot, because if I go twice as fast, the derivative should be twice as large. Now, I want to define a way of doing inner products so that it is still true that the derivative of the norm is equal to that. Now, why do I have this upper d? Don't worry about it. This is d over dt, and I will explain later why I need that different symbol. When again, it's just like before. If I have the one norm or the infinity norm, I'm doing something that may appear to be weird, but ultimately it's not that weird. Let me look at the Euclidean case first. If I have a two norm, I already defined for you this operation of log norm, and it comes with a natural inner product. If I have the one or infinity norm, I've already defined for you the one and infinity log norms. It turns out that I need to define these operations of inner products with respect to the one and the infinity norm. People, I'm not going to use the language inner product because it does not satisfy all of the properties of an inner product. It satisfies a weaker set of properties. So these are called pairings or weak pairings. And it's still true that if I were to take the derivative with respect to time of 1/2 the one norm of the curve x, that would be equal to x dot of t into x of t, where this pairing is the one pairing, this one up there. Does that make sense? What are these pairings? Let's just look at these together. These pairings are, you have a first and a second argument. You take the one norm of the second argument, y. You take the first argument, x, and you multiply there. Oh, and you take the sign, sign, so the +1, -1, or 0, of the second argument, and you do the transpose. Does this definition make sense to you? I give you two vectors. You take the one norm of the second vector, then you take the sign entry-wise of the second vector, and you do the inner product with the first vector. You get a number out of that. That is the one pairing, or the sign pairing, or the L1 pairing. People sometimes refer to the one norm as the L1 norm. Any questions? It is not commutative. The order is important. It is not bilinear. The intuition is that the Euclidean norm comes from the inner product on the Euclidean space. The one and infinity norm do not have an inner product. At most, they have an operation such as this one. There is a similar and complex definition for the infinity norm. I won't use it all that much, so I'm going to skip it. It's stated here. I'm only going to say, in summarizing this discussion, that on arbitrary norm space, vector spaces, you can define a weak pairing, always, it's always possible, that will have weaker properties than an inner product. So that's why I don't call it inner product. And it has a few properties. It is linear in the first argument. Well, it is sublinear in the first argument. There's a less than equal here. It's continuous. It has certain homogeneity properties. It gives rise to the inner product. And it satisfies the Cauchy inequality. It satisfies the curve norm derivative formula. So when you take the derivative of the norm of a curve, it's that inner product. And also one final property that always holds, and sometimes it's useful in calculations, is that it turns out that it satisfies, there is a relationship between the log norm that I introduced 10 minutes ago and this weak pairing that I introduced 1 minute ago. Now, to cut this long story short, I can finally go back and That's why I basically, now you understand why I kept this definition in gray, because I didn't want to drive you crazy with all of those definitions. Huh? But the point is that the one-sided Lipschitz constant can either be defined as the supremal of the log norm of the Jacobian, or if you have available, if you want to study this theory of weak pairing, basically what it's saying here, and let me do it in the case of Euclidean norm, so it's a little bit easier, right? It's basically f of x minus f of y transpose x minus y less than equal than b times the 2 norm of x minus y squared. So if you were working just with the 2 norm, that is the condition for one-sided Lipschitzness. The smallest number b that makes that equation come true for all x's and y's is the one-sided Lipschitz constant of the map F with respect to the two norm, right? This norm here. Again, sometimes people call this the L2 norm. If you are working with arbitrary norm spaces, then you use this more general definition. Okay, so I feel like this is a good moment to take a break. It's I spoken for another while. So let's take, we started at 2:30, 2:35. We will finish at 5. It's 4:07. Let's restart at 4:10 for the last 50 minutes.
Sorry, Professor. Before breaking, can I ask a question?
I apologize. Is there a question?
Yes, can I ask a question?
Please go ahead.
Okay. If I understand correctly, a weak pairing is another way to prove the contraction. I mean, as you told, contraction can be proved based on different metric for the distances.
Correct.
Okay. Can I ask that what are the advantages of this metric rather than the others? For example, if we use from.
Thank you for the question. So allow me to rephrase it. So there are two ways of defining. Well, you can always define it this way and show that the other is equivalent. But in any case, clearly, first you start with the definition and then you establish it. So what are the advantage of version 1 versus version 2? Well, the advantage of version 1 is that you don't have to even take the Jacobian of the vector field F. You just work with the vector field itself and you compute differences. In some cases, computationally, that may be advantages rather than having to take the Jacobian. They are equivalent. There are cases when you are studying the properties of contracting vector field where it's very convenient to use this characterization. So maybe you use definition 2, you check that definition 2 is correct, and then you perform the manipulations in the proof using property number 1. So it's convenient to have both in either examples to verify contractivity or in proofs to establish properties of contracting systems.
Thank you, Professor. I got it.
Thank you, Martesa. Perfect. Okay, so it's already 4:10, so I'll take 5 minutes. So let's start at 4:15. Yeah, so we can all catch a breath of fresh air.
Yeah, that's the question. We should be representing.
No, it can easily be negative. Yeah, sorry. Yeah, that's a type. Thank you. Yeah. All right. So time to start again. So yeah.
Is there a kind of relationship between the contractivity of the flow map or the vector and the log map? It's not related to kinds of estimates of the liberty in this machine condition.
Yes,
because you might think the lever is going to have at least part of the flow.
yeah. So this one-sided Lipschitz constant is precisely telling you the contractivity rate. That is to say, I'll write down formulas tomorrow, the rate at which trajectories come together. Yeah. Yeah, it's a detail that I had left out. So thank you. Yeah. So, okay, so we have studied this theorem that gives you conditions for contractivity in the continuous time case. And contractivity requires this property, either differential property, this one here, or this integral weird looking inner products called weak pairing. So in the literature, if you look at various articles that are studying either biochemical networks or neural networks or traffic problems, it turns out that depending upon whether you look at the 2p norm, the 1 norm, the infinity norm, you can write various conditions. In fact, in this table, there are 9 entries, 3 different norms, 3 different formulas. Whether I am using the log norm of the Jacobian, so which is that, or I'm writing the LMI characterization, or I'm writing the integral characterization without any derivatives. I could write, again, I could write either the log norm of the Jacobian Or I could write the equivalent with the linear program characterization. Remember that I told you that the log norm being less than 1 can always be written as an LMI in the 2 norm case or as a linear program in the 1 and infinity. Or I could use this weird sign weak pairing that is not a linear product, right? So we have seen for each norm 3 different equivalent conditions for a total of 9 conditions. I didn't write it out. This is a condition about the lambda max of the symmetric part. This is a condition on a certain linear program being satisfied. It is no surprise that in the literature, people use different names for these properties because depending upon how they were performing the analysis, they may have arrived at any one of those 9 independent formulas at any point in time without realizing that each one of these 3 are if and only if, so those are equivalent, right? Each row, they're all equivalent. And even from row to row, they're not equivalent because one is contractivity with respect to the 2 norm, another is contractivity with respect to 1 or with respect to infinity. They're not equivalent, but they're all part of the same theory of continuous time contraction system. Does that make sense? So 9 different formulas for not exactly, but pretty much the same conditions, continuous time contractivity with respect to the appropriate norm. Question?
Yeah, maybe are they influence or
Pardon me?
Are they influence only to take?
They are equivalent only if you can take, well, but as I was mentioning to you, provided your function is locally Lipschitz, you can take derivatives. But yeah, typically people would make sufficient assumptions on the differentiability.
It's one side of which is I can take it to focus.
If you want to define one-sided Lipschitz in general, you could use the integral equation, so you don't need to talk about derivatives at all.
Yeah.
But typically, systems are differentiable oftentimes, almost everywhere. And then if you want, you can write the derivative version of it. Yeah.
Is it true that one system is satisfies one of the 3, maybe the permanent dimension space satisfies and then our coefficients?
What is true is that if you satisfy this, then you satisfy also those other 2. Or if and only if with this comment about the differentiability. It is not true that if you're contracting in one norm, you're also contracting in another. It is not true.
The difference between contracting different norms is just the performance. The fact that they should contract because the norm are more conflicting with the other. They're eventually going to lead to. So
no, the difference of norm is the different shape of the level sets which are shrinking.
yes.
Now I can find matrices. I can give you an example of a matrix such that, and you give me 2 norms, P and Q, 2 norms, a norm P and a norm Q. I can give you a matrix. The log norm of the matrix is negative with respect to P and positive with respect to Q. We can do this example. We can figure it out. It's not a big deal. Does that make sense? It's not true that if the log norm of a matrix is negative with respect to norm P, it must be negative with respect to norm Q. All right. So for each matrix, you need to find the right norm. And remember, for a nonlinear system, you need to take the supremum of the log norm of the Jacobian. So now, for any given system, you need to find a norm such that at one point, the log norm is negative, but actually everywhere it has to be negative. So you need to choose your norm very carefully. Was there another?
Yeah, maybe there is one side, Minicourse is, for example, if it's L1 norm or 2 norm and L2 norm, one is always greater than the other.
That's not true.
Again, the simple thing, like most of the speed is in the speed case, yes, I mean, because here you have the long ones, it doesn't work.
Right.
With the speed case, I guess.
That may be true for vectors with constants. Yes, because you're starting with the concept that all norms in a vector space are equivalent with appropriate constants, right? Yeah,
I mean, it's a
that's right, with constants. I'll bring this for you tomorrow. Yeah. Yeah, allow me to keep going, because otherwise this will take too long and we can take it offline. All right, so now I have executed this first bullet item of my plan. So in the remaining 35 minutes, let me show you the other two. And then tomorrow we start with the book and I will send you the slide via email. Let me know if you want this slide. So first of all, how do I work now with vector field that are functions of time and of an input, which itself is function of time? Okay, as you have now by now learned, we are working in the world of Lipschitz constants. Lipschitz constant, one-sided Lipschitz, it's all that world. So now we have two spaces. We have the space where X lives, and we have the space where U lives. So let me assume that there is a norm in the space X and there is a norm in the space where U takes value. So the norm sub X and the norm sub U. So let me suppose that if I only vary X and I keep T and U constant for a second, my vector field has one-sided Lipschitz constant, which is at most minus C. And I want that minus C to hold uniformly in T and U. Does that make sense? So if you have a function, it's a function of some parameters. For each value of the parameters, I compute a one-sided Lipschitz constant with respect to X. And that number, unfortunately, if it's positive, it doesn't work. But if it remains negative, and moreover, it remains upper bounded by a negative number called that minus C, where C is positive. Okay, then I will have a number, and that number is minus C. So I have a contractivity rate C, and it's positive. And then the input U affects the state. My assumption will be that the input U affects the state, but does so in a way that is Lipschitz. So if the input U changes, the vector field F will change. The amount that it changes is upper bounded by L times the variation in the input. L. I want this Lipschitz constant to be computed with respect to U, with respect to X, uniformly in the other variables. When you have these two properties, so now basically you have two variables. You have variable X, you have a dynamical system in X, and you have some input U. You have there's maybe some unknown theta that affects the dynamics. The variation in the input U affect F in a Lipschitz way. With respect to X, your system is contracting infinitesimally. Well, then you obtain this ordinary differential equation. So again, on the right hand, on the left hand side, think of that as a time derivative. Maybe now is the time when I should clarify. Why do I have this D plus? What does it mean? So it turns out that the one norm and the infinity norm have a level set which is not smooth, right? Remember, the level set of the two norm is a circle. I should have centered this. Something like that. But the level set of the one norm is a diamond like that. And the level set of the infinity norm is a square, right? Or I can get a rectangle if it's weighted infinity norm. So it turns out that the norm of a curve, even if the curve is smooth, if the curve passes through zero, the norm of the curve is not differentiable to zero. It's like the derivative, it's like trying to take the derivative of the absolute value. The derivative of the absolute value is not defined at the origin, right? It's defined right before, right after. But if your curve goes through zero, you lose differentiability. So it turns out that there is a notion of Dini derivative, the Dini derivative of a curve that may be non-differentiable at the point. So for everything that you need to know, this is going to play in the course of my mini course. This is going to be the time derivative. But to be more accurate, if you have a problem of this form, you should invest a couple of hours of your time to study Dini derivative and then define everything with Dini derivative. So this formula here that I highlighted would be wrong if I were to put time derivative. It's the Dini derivative with respect to time. In practice, for the purposes of what I want to establish, the standard time derivative and the Dini derivative are going to have the same properties. So specifically, if the Dini derivative is less than zero, the curve is decreasing. That's still true. Does that make sense? All right. So actually, yeah. So there's a beautiful theory of Dini derivatives, and I'm gonna use them without defining them. And I will encourage you, if you want to be careful on these things, to look them up. Now, what does this ordinary differential equation say? This says that, look, there is a derivative of, let's call that the error. Let's call the distance between the two trajectories, the norm of the difference. I'm going to call it the error. The error is satisfying an ODE, which looks like E dot is minus less than equal than minus CE. So this is good because this means that the error as a function of time is decreasing exponentially fast or even faster. Because the solution to E dot equal to minus CE, the solution to this is error function of time is equal to error at time zero, exponential at minus CT. Now you should hate me because I used the letter E for two different purposes in the same slide. One was the error and the other one is the exponential. Forgive me. Let's do this. How about if I write exp minus CT? Are you okay with that? It's a little better. Forgive me. I didn't think about that. Error is E to the minus CT is E. So anyway, forgive me. So it's exponentially decaying with rate C. It turns out that when you have this differential inequality instead of an equality, there's something called the Bellman-Grunwald Bellman-Grunwald lemma. And the Bellman-Grunwald lemma tells you that if you satisfy this differential inequality, then it turns out that you will get an inequality there. So the error may decrease even faster than that. All right, so that's the good part. But of course, there is also a variation due to the noise, the error, the variation in the input U is changing. And so this equation is saying that, yes, you're decreasing, unless the input, the variation in the input is keeping you away from zero. So you have, essentially, you have plus L, the forcing term, the norm of the variation in the input. So the two parameters, minus C and L, they come around like this. Now, this equation star is a differential inequality. If I want, I can integrate it with this Bellman-Grunwald lemma, and I get something like this. So I know this looks like quite a bit. Basically, it's saying that the distance between the two trajectories is equal to an exponentially decaying term, e to the minus CT, which multiplies the initial error, the initial distance between the two trajectories. But then I have a sum plus, and it depends upon the difference between the inputs. If you use the same inputs, of course, the two trajectories are going to come together, just like before, right? Before I had a picture that showed two trajectories coming together. They were starting at two different points, and they would come together. But now, if the two trajectories are subject to different inputs, they cannot come together Because maybe I have one trajectory pulls me right, one trajectory pulls me left, and the two trajectories, instead of coming together, they're becoming separated a little bit, right? The separation due to this difference is to this difference between the inputs. Okay? Perfect. And how much can that be? That's given by this constant here. L over C, which multiplies 1 minus CT. So by the way, if I plot that 1 minus e to the minus CT, this number starts at 0 and it goes to 1 as a function of time t. So if you want, you can even just upper bound this by L over C. So this is saying that the difference in the error is exponentially decaying due to the initial condition. And then it has a term, let's just call it L over C for simplicity, times the variation in the input. So in control theory, people call this input to state stability property. The input affects the state, but in a bounded way. There's an error due to the initial condition that goes to 0. And then there is a constant here, which multiplies the variation in the input. This constant is the Lipschitz constant over C, the Lipschitz constant with which the input affects the state, divided by the contraction rate. This makes an enormity of sense because if you go back to the assumptions, what were the assumptions? The assumptions were that L over C. L is how large is the impact of the input divided by how stable is your system. If your system is very stable, the denominator is very large, and then this effect is small. Or if you keep C fixed and you imagine a very large L, if your input is generating a lot of variations, of course, then L over C will be larger. So the size of the ultimate distance between the two trajectories is grows proportionally with L and decreases inversely proportional to 1 over C. Question?
What does UX and Y would be like?
What is the question?
In the spring, UX and Y.
Oh, this is the input for the first trajectory and the input for the second trajectory.
Okay, no,
Right. So I have two trajectories. I should have been more careful. Let me say it better. I think I actually did write it, but I did not pronounce it. So it's my fault. Forgive me. So I have two trajectories, X and Y. X starts from initial condition X at 0. Y starts from initial condition Y at 0. X is subject to an input UX, and Y is subject to an input UY. My fault. Thank you. I apologize. I should have said it. As you know, I lost my suitcases, and I'm so much hoping to find them, but I cannot read the message.
Sorry, maybe already you said it, but
Question.
yeah, sorry. You're using the subscript X and U for the norms. It means that you can use different norms, like the 2 norm and the infinity norm, or the subscript have a different meaning.
I apologize. Your voice arrived very muffled, and I could barely hear you.
Okay, sorry. Better.
Yeah. So these norms, this X norm and U norm are arbitrary. You give me a space on the state space X, and then the input space U, and they're different because U does not need to take place in the X space. And I have 2 different norms. I don't know if I answered your question.
Okay. Yeah. Thank you.
Oh, yeah. And I see another question by Adriano on the meeting on the chat page. And yes, it is exactly the same derivative as in Khalil. It's called the upper right Dini derivative. It's not just upper right derivative, upper right Dini derivative. And it turns out there are 4 Dini derivatives, and the one that you need for stability purposes is the upper right one. There's the upper and lower, right and left. And they have various properties. It's a very elegant little theory of that. It's not a very complicated set of concepts, and it works. All right. So here, right, okay. So we have two trajectories, two initial conditions, two inputs. Despite the fact that you have two different initial conditions and two different inputs, you can still write a bound like that, telling you how far is one trajectory from the other. This type of bounds are called incremental input to state stability bounds, and they're very helpful. I will show you an optimal control application where I use these bounds. Typically, these two trajectories could be, for example, a zero input for the trajectory starting at an equilibrium, and the other trajectory could be a trajectory starting in the neighborhood of the equilibrium with some noise pushing it around, right? So you basically have a nominal evolution, an ideal evolution, and the real evolution. And now it's really an error, right? X minus Y, it's really like equilibrium X star versus some other trajectories. Another idea could be you are doing forward Euler integration. One is the exact solution of the ODE. Trajectory X is the exact solution of the ODE. And the other is the trajectory constructed by your Euler integrator. You take a step, a step, a step, a step, a step, but you remain nearby. Right. Okay. Perfect. I will skip these ideas. Now, let's suppose now that instead of having a nominal system, let's generalize what we said so far. Instead of having a single nominal system, let's suppose I have a system with unmodeled dynamics. So you could say, oh, Francesco, why don't we think of this as an input U? No, because this depends upon the state. So it's not a subject, it's not a system subject to an external input. This is unmodeled dynamics. It's different. It's a different kind of perturbation. Before I could have had some noise hitting me, an exogenous noise. Now I have, state-dependent noise, so it's unmodeled dynamics. It's not the same. So let's suppose that, as you can imagine by now, my nominal vector field F is infinitesimally contracting with rate C, which is to say, the one-sided Lipschitz constant of F is upper bounded by minus C. Now, minus C is the rate of contraction, right? Two trajectories come together with the rate minus e to the minus ct. So that the rate, it also has a notion, an interpretation as robustness. It goes as follows. Let's suppose that the one-sided Lipschitz constant of the unmodeled dynamics G, so that's how bad the stuff you don't know is. Let's suppose that's upper bounded by a number, like a disturbance. Let's call it lowercase d. So now you are contracting with rate minus C, or with rate C, but it's a minus C, right? And D. Now, the condition is that you need C to be greater than D. In this sense, the contraction rate is a notion of robustness. If you are more contracting than the size of the disturbance to which you're subject, then the full system, not the real system, not just the nominal, but the nominal plus disturbance, is still contracting with rate C minus D. So that's the theorem. The theorem says, hey, guess what? If the disturbance is less than the contraction, then F plus G is still contracting, infinitesimally strongly contracting, with rate C minus D. So you lose some of your rates, you lose your guaranteed convergence rate, but it's still exponentially convergent, just more slowly. Now, yes. It could be. Now, typically your feedback controller is stabilizing.
What I'm saying is that these equations in the unmodel analysis also control the density. I can see it also as I control the density state. So when I'm talking group, or when I'm talking about here, is also
It could be, right, but usually what may happen is the following. That you have, what really might happen is the following. You have a dynamical system and it may be unstable. You design, now the real system is very complicated. Maybe the real system has 100 variables, but you don't have an exact model with 100 variables. Maybe you have some knowledge of the system. You design a controller for the system that you know, for the nominal simple system. Now you close the loop. When you close the loop, so you apply the control. Now your simplified nominal system plus the controller is stable. The nominal system plus the controller is stable, but there is all the dynamics that you have not modeled. For example, you have a robotic manipulator. You have a robotic manipulator and you assume that each of the links is rigid. Each link in my robotic arm is rigid. Now I move it around. It's on a controller and it's stable. But the reality is that the robotic arms are not rigid, they're flexible. There's some dynamics, the flexibility, which I don't want to take into account. So the flexibility is the disturbance here. And F would be the nominal rigid body with the controller. Or maybe I have an aircraft that is flying. It's hard to model the effect of all of the aerodynamic noises. So we design a nominal controller to keep the aircraft flying steady, and then it gets hit by the disturbances. And maybe everything vibrates, but still, there's a nominal dynamic plus the disturbance. All right, plus due to the flexibility of the aircraft. All right. Now, the other property that I want to show you is the following. So we stated the Banach contraction theorem that said that if F is contracting, and let's suppose it's time invariant for a second, because the Banach contraction theorem is for time invariant systems, time invariant. Huh? So the Banach contraction system, there exists an equilibrium point, all trajectories converge to it. That's for the time invariant case. So for a second, now in the second clause here, let's suppose that both F and G are time invariant. Huh? So I now have X dot equal to F of X plus G of X. But F is contracting, which means that there exists a unique globally exponentially stable X star such that F at X star is equal to 0. So F has a globally exponentially stable equilibrium. Now I apply a disturbance. And I'm telling you, F plus G is still contracting. Okay. But if it's still contracting, then there must exist another point, let's call it X double star, such that F at X double star plus G at X double star is equal to 0. A new equilibrium. So I have my nominal network system, it has an equilibrium. Now, the real system has more dynamics. There's more stuff that I don't know. If I knew it, I could analyze it, but I don't know how to analyze it. Or maybe it's not contracting, so I'm just going to upper bound it in some sense, right? Provided G is less than C, so if the disturbance is less than the contraction, then the equilibrium point will move. It moves from X star to X double star. How much does it move? How far can you go? It turns out that it goes far, but not very far. Its amount it moves is upper bounded by the value of the disturbance at X star divided by the remaining contraction rate, C minus D. So the more contracting it was and the smaller was D, the larger is the denominator, and so you don't move very much. Well, again, it depends upon the size of G. If G at X star is immense, then of course you want to move away. Does that make sense? So this tells you that for this 6-point problem, for this Banach contraction, even if you have uncertainties, they push you around, but the amount you move around depends in a Lipschitz continuous way on the disturbance. Okay. Perfect. Of course.
You said that the bound for time variances. If the system is time variant, but it's strictly constructed before you get the time, then can we apply the theorem way?
The problem is this. Let me show you an example right now. Suppose I have a strictly contracting system uniformly, and I apply a time varying disturbance to it. Well, then it doesn't need to be at an equilibrium. I mean, for example, suppose I give you even a linear system, x dot equal to minus x, clearly contracting with respect to my norm is the absolute value. Because here, let's just take the scalar case. I'm a scalar system. If I apply cosine of t here, what do you hope to get? Cannot go to an equilibrium, right? You know, I could also apply a ramp. Now this goes to infinity. The solution to this contracting system with this unbounded input will go to infinity. The solution will be a ramp. This is a linear system subject to a ramp. The output will be a ramp plus transient. It doesn't matter. This is going to infinity. So as soon as you start to play with time varying things, there could be unbounded. If here's even worse, x dot equal to minus x contracted plus t squared. No, I don't need t squared. I need something faster. Plus a function of time that has a bounded escape time. Then x will not even go, the solution doesn't even exist for all time. It'll integrate infinity, right? All right. Now, so this was not the right idea. All right, fine. So one more example. Let's talk more about this time varying case because it's a little tricky. Time varying contracting systems, you need to be careful. The main theorem, two trajectories will still come together, but all right. So here's a useful version. Suppose that I have x dot equal to x dot equal f of t, comma x. There are two examples. The example in the picture is slightly different, not very different, slightly. So suppose that f is, and here I should have written uniformly in t. So at all time t, the one-sided Lipschitz constant of f with respect to x is minus c. And suppose that with respect to the time variable appears in a periodic way. So it's as if there was a periodic perturbation. So I am applying a periodic perturbation. A specific way would be if I were to take a vector field of the form f of x comma u, and then I let u be a function of time, and it's periodic with respect to time. So that it's really exogenous forcing, periodic forcing. Now, what does the theorem say? The theorem says is that there exists, so, you know, here I'm imagining that I have a nonlinear system with an input, but the input is periodic, right? I drew a picture like that. It's just a nice sinusoid. What comes out is that there exists a unique periodic trajectory to which all other trajectories converge exponentially fast with rate c. There exists a unique periodic trajectory, not a unique fixed point, a unique periodic trajectory to which all other trajectories converge exponentially fast. All right, so that's what this nice theorem says. There exists a unique periodic solution, same period as the input, right? And all trajectories converge to that particular trajectory at a rate e to the minus ct. So here you see I'm writing the distance, well, the norm of the difference, right? The distance between an arbitrary trajectory and the periodic trajectory. And this is the error at time zero. This is the position from which I start and the position from which the periodic trajectory starts. And all of this is decreasing with rate e to the minus ct. Exponential decrease. Very nice. So for the time invariant case, there exists a unique globally exponentially stable point, no, a fixed point for equilibrium. For the periodic case, there exists a unique periodic trajectory, globally exponentially stable. If you have an arbitrary time dependency, all that is true is that any two trajectories will converge to each other. That is still true, but I cannot say anything about what they do. Because, as I showed you, they could go to infinity, they could remain bounded depending upon the input. If the input goes to infinity in bounded time, they could go to infinity in bounded time. So then the solution doesn't even exist for all time. So we just cannot say more. Now, how tired are you? Should I break, or do you want me to speak for another 7 minutes? Shall I continue? You look like you're happy. Okay. So let me start this setup. And if I run out of time, that's okay. It's not a problem. It looks like I have my hand raised. I wish I could unraise my hand, but I don't know how to do it. The first option here? Oh, you're right. Okay, fine. All right. So I mentioned to you that I'm very interested in network systems, or network system defined over a network. At each node of my system, I have a dynamical system, right? And they're interconnected. So in other words, the solution, if I write this x5 dot could be a function of x5, but maybe if this is x1, it also depends upon x1, and then it's x2, depends upon x2. This is x3, depends upon x3. But this is x4, it does not depend upon x4 because there is no edge. Okay, so what else is missing? What do I have? x6, x7. All right, fine. x6, x7. So this is the meaning of the edges. The edges mean the dynamics of each node depends upon itself and the values of the state that are neighboring. Okay, now you already know what I'm going to assume. I'm going to assume that at each node, my dynamics is contracting, right? That's a natural assumption. I am going to assume that I have contractivity here, 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 here. So I'm going to have minus C1. Well, let's just write C1. Goodness gracious, X1. C1 is the contraction rate there. C2 is here, C5, C3, C7, and so on and so forth. Right? I'll have a contraction rate at each node. But okay, but that doesn't make sense yet. Before I talk about a contraction rate, I need to have a norm. Now, these dynamics could be defined over similar nodes. Each node has 4 states, 4 here, 4 here, 4 here, 4 here, 4 there. But it could also be that they have different dimensions. It could be that I'm interconnecting the power plant with the solar panel, but then the dimension of the dynamics is different. So it doesn't, the theory that I'm about to present for you allows you to use different dimensional nodes, and therefore also the norms at each node could be different. So it's a very general setup. Maybe the nodes are all more or less identical. Perfect, use the same norm if you want at each node. But in general, you may have different norms. So you may have n subsystems. Each subsystem takes value in R and I, so it has capital N sub I variables. And I have a norm sub I for the ith subsystem. Does that make sense? I have lowercase n subsystem. Now, what do I want to prove? I want to prove contractivity for the interconnected system, right? Because I said to you at the beginning of this lecture, I said, I want to say, when is it true that the interconnected system is contracting if each of the modules, each of the subsystem is contracting? Does that make sense? If I want to talk about contractivity on the full space, well then I need a norm on the full space, because with respect to what norm is it contracting, I need a norm, right? So now, if I tell you that you have 2 states, x1, x2, and you take the norm of one, let me say it better, let me write it better. you have x, and you write x as x1 and then x2. And then you can take the norm of x1, 1, oops, and you can take the norm of the second. So now the subscripts 1 and 2 are not norm 1, norm 2, are the norm of state 1 and the norm of state 2. I need to take these two numbers and map them into a single number. I need to aggregate two norms and get a single aggregated norm, right? I don't want to have a vector. I want to be able to aggregate. If I have n subsystems, I need to define an aggregating norm of Rn. Maybe the aggregating norm could be the one norm. But the one norm of n numbers is the sum of the absolute value of n numbers. But if each of the numbers is a norm itself, it cannot be negative. So then the aggregation is just the sum of the norms. But that's not the only way I could do it. I could use the two norm, which is to say, I could say, okay, take x1, 1 square plus x2, 2 square root. I can aggregate the norms in many ways. It doesn't matter. I can aggregate them, even in hybrid ways. Suppose that I have a third state, x3. You know, this is also an aggregated norm. This is also works. You take the two norm of the first two variables plus the norm of the third variable. This is, you can also show that this is also a operation on the full space that satisfies the axiom of the norms. It's a norm. It's complicated. All right. Now I'm ready. What do you expect me to make as assumptions? I hope that by now I'm not surprising you in any way, shape, or form. Because here's what happens. I have a dynamical system for each node I. How am I going to write it? Well, I'll write Fi, xi dot. It depends upon what? Xi. And then it depends upon some of the other states. Have you guys seen this symbol? Have you guys seen minus I? Minus I is it means to say 1, 2, all the way to I minus 1, I plus 1, n. So minus I is all indices except for I. It's a notation, it's a convention that was introduced in game theory. If I look at ith agent, what is the state of all of the other agents? Minus I. It's a trick. It doesn't really mean it's not really the number minus I. It's not like -3. It just means to say all of the others. Okay, so I have a dynamical system which depends upon the states and something else exogenous, external. But then, what are the standard assumptions that we've made when I have an input? Lipschitz. Okay, so here are my two assumptions. I'm going to assume, unsurprisingly, that the ith state is contracted infinitesimally. So I have this condition. So uniformly in the state of the other nodes, my vector field at node I is contracting, and it has a contraction rate Ci. So the one-sided Lipschitz constant is at most minus Ci, uniformly no matter where the other states are. Then, if I keep xi fixed, and I look at what happens when I change xj, then I am going to assume Lipschitz dependency. So, if I am looking at state I and I vary state j, this variation in j has a Lipschitz effect on how the vector field at I varies. What is that constant? Well, so I have minus C, I, and then I have Lij. Earlier, I had only L in the, remember we did the case of an input Q. I had minus C, L. Here I have minus Ci, and I have to have Lij because it's how J affects I, right? And there are n such states. So I and J are going to run from 1 to n. But by definition, Lii, I'm going to set that to 0. So I don't have a self loop of disturbance, right? So the dependency of Fi with respect to I is inside Ci. Okay, so I have a network of contracting systems. Each system is contracting, the interconnections are Lipschitz. And now, how many parameters do I have? How many parameters have I defined? Well, I have at each state, I have minus Ci, but then I also have this all Lij. So here's what I'm going to define. I'm going to define a matrix. I'm going to put all of these numbers in a matrix because they fit perfectly right in a matrix. How do they fit? They fit because the contraction rates, I'm going to put them on the main diagonal, and there is n of them, just like the entries on the main diagonal of the matrix. And the Lii, they don't make sense. I set them to 0, so they don't even exist. Forget about them. But the Lij, where I is different from j, they just very nice, right? They just fit upper right, bottom left, and I get a matrix with the contraction rate on the diagonal, minus the contraction rate on the diagonal, and the Lipschitz gains, right? The interconnection gains of the Lipschitz, the Lipschitz constant of the. I'm tired, and we passed the hour, so let's finish this. So that matrix, I will call it the gain matrix, and I need that matrix to be Hurwitz. You guys remember what Hurwitz means? You know, it means that the eigenvalues have all of the eigenvalues have negative real parts. Negative real part. A matrix is Hurwitz, a square matrix is Hurwitz. You better not try to do it for a rectangular matrix. A square matrix is Hurwitz when all of the eigenvalues are negative. That's my definition. I have negative real part to be precise. Then what I will show you in detail tomorrow, and when I say tomorrow, I mean to say the next business day, which is Monday, is that if this matrix of interconnection and contraction gains is Hurwitz, then there exists a norm and there exists a contraction rate such that the interconnected system is contracted. Let me just little example. Minus C1, L12, L21, minus C2. When is this matrix Hurwitz? It is Hurwitz when C1, C2 is larger than L12, L21. It's easy to check. I will let you check it. You know how to check the Hurwitzness of a 2x2 matrix? You have to check that both eigenvalues have negative real part. You compute the trace, which is the sum of the eigenvalues. This is negative. Yes, because minus C1 and minus C2 are both negative. The sum is negative. So the sum of the two eigenvalues is always negative. In order for both eigenvalues to be negative, you need the determinant to be positive. So you do C1, C2 minus L2, L1. The determinant needs to be positive. This is the condition that you get. That condition says that the product of the contraction rates must be larger than the product of the Lipschitz interconnection constants. So these constants sometimes are the gains. How much does one affect two? How much does two affect one? These gains needs to be smaller than the contraction rates. So that's what I will start from on Monday. But that's how simple what I like about this, and let me re-emphasize it. These are very natural assumptions. If you understand the discussion earlier about the input to state stability, the way in which the input was getting into, and those bounds, then this is just a natural extension, right? Okay, perfect. Thank you. If you want these slides, I will post them on my website, and we'll go from there. I'll see you on Monday morning, I think. Yeah. Okay. Bye bye, everybody.